we're going to look at two experiments. The first experiment, we're going to take a ring and we are going to drive a north pole down on that ring. And as I do it, I want you to answer this question. How does the dipole have to be set up in that ring to fight that motion? Would this turn into an electromagnet with a north pole up or a south pole up? A north pole up. Now, which way does induced current have to go around this loop to make that kind of an electromagnet? Right-hand rule number 3, it's got to go counterclockwise like that. Now, I need you to think about the center of the loop. The center of the loop. And think about the two different flavors of flux, of field lines. Okay? I got the external flux due to the bar magnet. I have the internal flux due to this current that's induced. Now, what direction will the external flux point through that loop? If I've got a north pole, the field lines come out of the north and then spread. So what direction do they go through that loop? Down. And there aren't very many that get through the loop because I'm so far away. Now the induced current goes around this way, so induced flux or induced field lines are that way. Notice that they're opposite the external flux. That, it turns out, is not important. I just wasted your time. Now as that north pole gets closer and closer, the external flux gets bigger and bigger. Okay? Now, one more experiment. This time I'm going to take the north pole and I'm going to pull it away. Now, this is going to turn into an electromagnet. What am I going to have here up next to the north pole? Will it be another north or a south? South. A south to fight the motion. And that means that induced current is going to have to flow the other way, clockwise, in order to make this dipole. Okay, it's going to have to go around that way. Again, let's think about the flux at the center of the loop. I've got external flux, that's due to the bar magnet, coming out of the north. My induced flux is caused by this. Notice that the induced flux is in the same direction as the external flux. That is not important at all. Okay? Let's put these side by side. In the case on the left, I start with a little bit of flux down, external flux, and then when the bar magnet gets closer, I have more flux down. The change is what I have to add to this short vector to get a long vector. And that's the plus sign right there. Now notice that the induced flux is opposite that change. That's important. That matters. If we look at the other experiment, we start with a lot of flux down, because I start with the magnet close, and as I pull it away, I have a little bit of flux down. My change vector is what I have to add, there's a plus sign, to this long vector to get a short vector. And sure enough, the induced flux, caused by the induced current, is opposite that change. That's the piece that's important. This induced flux will always be in the opposite direction of the change in external flux. Always, always, always. As I said, copper loops hate change. They fight change. They fight it with a passion. I think of these copper loops as Republicans. They don't like change. Didn't like Social Security, Medicare, the whole 21st century. However, these are like Republicans in New England. They don't win, they just fight. Okay, these are like New England Republicans. Okay? Have I painted a picture for you? All right. Good. Okay. Now you need to know, Mitt Romney is one of my best friends in the world. I mean, When we were in school, we were his nannies, my wife and I. Whenever they left town, we went into their house and took care of their children. And they are excellent, wonderful, wonderful people. I didn't vote for him.